and visualizing LiDAR in GIS. How many people are already familiar with LiDAR data to some degree? How many have heard the word LiDAR before? All right, most everybody, not everybody. LiDAR is a really cool topic, really neat thing to bring in and use in GIS. What? All right. So you have all the data is already on these machines. So what I'd like to do today is give you basic skills in bringing LiDAR into ArcGIS. So what we're going to do is you should be able to create an Alias Dataset by the end of today. We'll talk about what that is. It's a way of bringing LiDAR data into ArcGIS. See the different tools available for visualizing the data. Learn how to construct digital elevation models, digital surface models from our data here. We're going to skip classifying point cloud data, but show a variety of examples of how you can use this in analysis workflows. So the outline for today, we'll give a quick introduction and then mostly hands-on through a few different activities here. So some of the applications we have today, depending on time, we may not get to all of these, but have examples to show you how to determine canopy heights in a forest out of LiDAR data, delineate watersheds or drainage basins, and perform viewshed analysis. So hopefully, I think, how many of you are in forestry, or are you the entomology folks? Anybody in forest resources or anything? Kind of. Wildlife, okay. So we'll see our tiger bird again, if you remember from a few weeks back. So what is LiDAR? Does anybody know right away? What does that word even mean?
Imaging detection, something radar?
Light detection, imaging radar, yeah. Right, so it's light detection and ranging. Sort of like radar is radio detection and ranging. So LiDAR is a remote sensing tool. So it's going to measure something from a distance. And it uses pulses of light or laser pulses to take measurements. And so what it's used for is mapping, say, the Earth's surface or features as a three-dimensional point cloud. So here, our spinning donut, if you imagine we take a donut and then set up some origin, some three-dimensional origin, and we measure the distance from that origin to all these different locations on the surface of our donut. And then store each of those individual measurements with an X, Y, and Z coordinate. We could then map those or view them in 3D, and we get this point cloud representation of the surface. So what you often see when you look at LiDAR data are really colorful pictures here, but you can see you can map both structures, terrain, built features, or natural landscapes. Basically anything on the Earth's surface can be mapped using LiDAR. How many of you recently saw in the news that, pull it up here, this game changer archaeological discovery here? So there in Guatemala, people use this laser scanning technology to map through the forest canopy and discovered all sorts of new buildings, basically this whole lost city underneath the surface of the forest that just wasn't visible before. So this is a very powerful and unique tool, which has lots of cool applications like finding lost structures here. And we'll get with the skills you'll learn today, you'll be able to visualize your data just like you see here in these displays, and then understand how this LiDAR technology is able to detect things buried under the forest or covered with the jungle canopy here. So LiDAR is light detection and ranging. It's this tool that emits laser pulses to measure the Earth. The data we're going to work with today are airborne LiDAR data. So they were collected from a plane flying over some area. So airborne LiDAR is collected by mounting this laser scanning device, this instrument, to the bottom of a plane. So this laser scanner, or LiDAR scanner, is going to emit all these laser pulses, which then go and bounce off of the ground, off of trees, off of buildings, off of whatever, and then that energy is reflected back to our plane. And so we know how fast that laser is traveling, the speed of light, so we know by how long it takes from that time of emission to the time of return, we can figure out exactly how far away that reflecting object was. So what's really cool though is these scanners do this hundreds of thousands of times every second on the line. So this scanner is continuously rotating and emitting all of these pulses, which map out these slots you see here along the bottom of the ground. So our first piece of information we have is how far away it was from our scanner to whatever this laser pulse bounced off of. And that's ranging or range finding is what gives us that distance. The next instrument you would have is some GPS that's mounted to the aircraft. So now we know where our scanner was located relative to the Earth. So we know where our scanner is located and we know how far away this reflecting object was, but we don't know in which direction it was. So there's also this inertial measurement unit, or IMU, that gives you the orientation of the scanner as it emitted that laser pulse. So combining these three sets of information together, the position of the scanner, its orientation, and the range to the object, now we know the X, Y, and Z coordinate of that point.
So what is the relative error in each of these LiDAR points?
You mean like how accurate do you know where that is? Horizontally, with a lot of these, if for airborne, you're probably in the centimeter to decimeter total accuracy. Vertical is a little more, maybe a few tens of centimeters generally. So a lot of it depends on how accurate or really how expensive your GPS and IMU are, and how detailed you can make that measurement, or how accurately you can make that measurement. Because these scanners are emitting and collecting hundreds of thousands of points per second, we also get this very dense set of information. So potentially, centimeters, or say a few tens of centimeters between every measurement. So if you think of normal terrain measurements made by satellite, they may have a 30-meter resolution. Here we can get, say, sub-meter resolution elevation data. Does this process make sense? Any questions right now?
Just out of curiosity, how does it go through the canopy to measure the volume?
Yeah, we'll see exactly how this works, but because we're emitting light energy, we think of it as a pulse, but by the time it actually hits the canopy, there's some area of coverage. Some of that energy penetrates through the leaves. The surface isn't totally opaque. Some of that energy can penetrate down through the canopy and hit the earth and reflect back from the ground. And we'll see in a few more slides how we filter out our data to remove just those measurements. So how do we collect these data? There's lots of different ways we go and get our LiDAR data. We can mount our sensors to aircraft. We can also put them on drones or unmanned aerial vehicles to fly around places we can't easily reach with a plane or a helicopter. You can mount them to cars and drive these things down the street. You can put them on a tripod to do scans from a single orientation, say scan your friend here in the corner. You can put them on trains, on boats, on satellites orbiting the Earth, or even on spacecraft that visit other places like Mars. So there's lots of ways we can collect our data. In terms of applications of the data, this is my short list here. I think the key takeaway from it is anytime you need detailed and accurate 3D information about the Earth and its features, you probably have some use for LiDAR data. So the images here highlight some really unique use cases. This is actually on the surface of Mars. This was taken with which satellite exactly. This is a very colorful visualization of LiDAR data in the Pacific Northwest. These are braided stream channels. Here in the lower left corner, this shows us a really neat application of LiDAR data in disaster management or just understanding areas that have been affected by disasters. So this was after Hurricane Sandy there in New Jersey. Just after the hurricane finished, they were able to go and fly, collect LiDAR data, and really understand the impacts or the extent of hurricane damage. So in disaster response, we can use this. Collecting data for mines up here in the upper right corner, estimating your slope stability. If you're interested in historic preservation, a lot of preservationists use LiDAR data, or city planners and architects or civil engineers. Here, this bridge in the lower right corner. So does anybody know right away what they might want to use LiDAR for? Scott, you said you need to learn it. What do you have in mind?
Mainly visualization of elevation services.
Okay. Anywhere in particular you're interested in?
Up in the mountains.
Mountains, cool. Anybody else?
Just forest regions like canopy, gaps, and things.
Mm-hmm. Oh yeah, foresters love LiDAR data. Any others? All right. So let's talk a little bit about the way you would find LiDAR data, say to download from the USGS or some other agency that provides it. The industry standard way to receive that is as a binary file with a .las extension, or what I'll just refer to as a LAS file. And this is a format specified by the ASPRS, or the American Society of Photogrammetry and Remote Sensing. And this table here shows not exactly the way the file is laid out, but it gives you an idea of what it has within it. There's a header that tells you information about the scanner, the coordinate system, all this stuff, but really it's just a table of the coordinates of all of our points, X, Y, and Z. And then there's also some properties associated with each of these points. And some of these properties come from the measurement from that LiDAR scanner itself, and some of them are added as a post-processing step. So we'll talk about what the intensity, return, and classification are, and whether or not your data have color information. There's lots of other formats you'll see out there. The zipped LAZ is the counterpart to the LAS. It's commonly the one you'll download your data in because it saves memory. An individual LAS file you would have is probably on the order of a few hundred megabytes. So these data sets are fairly large. They take up a lot of storage space. So the LAZ format generally reduces it by a factor of 10. You can get the data in text formats, in an ASCII file, and there's lots of proprietary formats. So different vendors or different instrument manufacturers may have their own proprietary formats, and there's lots of other in use through different software. Yep.
If the X coordinate is position. How is it only one?
What she's saying is that there's something wrong with this slide and that the y coordinate of 94 is impossible. So.
No, because the Y is the orientation, right? But X is a spatial coordinate taken with a GPS.
So the X and Y here would be like your latitude and longitude, or an easting and northing. And so, and then the Z is the elevation.
Yeah.
But the y is impossible nonetheless.
Oh, on point N here. Yeah, you're right. I do have a type of 94 degrees, which is somewhere in space. Thank you. All right. I'll have to fix that before the afternoon session. So some of our properties here, the first one I want to talk about is this classification. And so the classification is a standardized label attached to the point that describes what that reflecting object or surface was. These are standardized. They are determined by the ASPRS. So if you have raw LiDAR data, they don't have any classification associated with them. So if you go out and collect the data or just get raw LiDAR data, there's never going to be a classification associated with it. This is done as a post-processing step. But commonly you would see things like the ground. So this point reflected off the bare ground surface. You might see vegetation codes or buildings or water or other things. So how is this useful to us? Let's say we have our plane with our LiDAR scanner. We go and collect this LiDAR file, and we're collecting points or measuring distances. Some of these points represent the ground surface. Some of them might have bounced off of trees, off of houses, off of buildings. But if we're interested in, say, just the ground elevation or the terrain itself, we can filter out and look at just those points that have a ground classification code. So we're going to take our points that bounce off of that, just off of the earth. We're going to remove everything above it. And then we can, say, connect the dots or really interpolate those points and create this digital elevation model or digital terrain model. So here's an example data set. I hope it looks familiar to everybody. Everybody know what we're looking at. We're sitting right about here up in Cooper Library. So this is the data we'll be looking at today. If we filter out and keep just those ground classified points, this is what our data set would look like. So we've removed trees, buildings, anything else. Then we can, say, interpolate and have a surface, an elevation surface here. And that's just our ground elevation model. Excuse me. Does that make sense? And so what's really cool about this is that we have a very high resolution data set, especially compared to, say, satellite elevation data. Another property you would see is the return. So this is going to be a number attached to each point. And so as this laser is emitted, if it bounces off of something that's totally opaque, like a building or the ground, we would just have one reflection. But here, if we have, say, a tree, part of that energy could be reflected from the top of the tree, from the canopy. Part of that energy may penetrate through the leaves. So we can actually have, say, another reflection coming from within the tree or here from the ground surface. Some of that energy may actually reach the ground and then reflect back up. So here we have the potential for multiple returns in our data. And you'll commonly see the last return comes from the ground surface. Questions on that? Does that make sense?
So the scanner is going to record these as essentially the same location?
Same location except different Z value. So this is how you're able to see through trees or see through a jungle canopy. Is that we're going to keep or remove anything. Ahead of myself here. The way we're able to see through the canopy here is we're going to remove anything that wasn't a last return.
So in the example you showed us before, it appeared that you removed some of the buildings.
This one?
The next one, I mean, you have to go back. So aren't some of the buildings removed? Are they the little white things?
So this is gaps from where the buildings are. So these are just our ground classified.
But there wouldn't be a last return because the building would be a hard bounce, right?
It would be a first and last return.
Okay.
If it came off of a building, a first and last.
I'm just trying to figure out how you remove buildings, but you'll tell us later.
Remove buildings, we're only going to keep ground classified points.
Okay, I'm just saying, how do you differentiate between a building and a ground because it's the same, hard return, right?
Oh, sure. So this is different algorithms applied to the data to tell you if it's the ground or non-ground.
We're not going to cover that today.
No, there's an example of using LAS tools in the tutorial. People who are watching remotely don't have access to those, so I'm not going to cover it. But it is available to us, and I can describe how it's done, at least in a hand-waving way. Going back to our returns here, if we filter out our data and keep just the first returns, our first returns would be points that have bounced off of the highest point in an area. So where it's the ground, we're just looking at the ground, but if we have, say, buildings or trees, this first return surface tells us what's highest in an area, and we call that a digital surface model, or a DSM. And so these can be useful for all sorts of other applications. Going back to our Clemson data here, if we filter out and keep just those first returns, we basically have that same picture. But then if we interpolate those points to a surface, here shown with some vertical exaggeration, we see we're keeping things like our buildings, our vegetation, as well as the ground surface. Some other properties you might see out there, color information. Some scanners will also record color. This is generally another post-processing step where they're actually overlaying an image on the point cloud and basically grabbing color from the pixel of the picture. Intensity is one you'll often see. And intensity is the strength of the returned signal in watts per unit area. And so intensity is used for things like automatic cover delineation. So say differentiating between pavement and grassy areas, for instance. It depends on a lot of things, like how far away this reflecting object was, the power of the scanner itself, as well as the properties of the reflecting surface. But there are algorithms that will take into account intensity data for some sort of analysis. So any questions on the properties before I go any further? All right. So if we want to bring LiDAR into ArcGIS, the way we do that is through a data structure called the Alias Dataset. And so this is essentially a pointer file. It's going to tell the software where you have a set of files with this .las extension on your machine. So ArcMap doesn't work directly with these binary LAS files. So our LAS dataset is the way we're going to bring those in and use them for analysis. And there are tools through the 3D Analyst extension and the LAS Dataset toolbar. We can display our data in ArcMap, both as a point cloud or do on-the-fly interpolation of the surface, both in 2D and 3D. And so there are tools we can quickly filter our data based on their classification or on their return number. What's a really important step that I'll show you is we need to calculate statistics out of our data. So really it just reads through each LAS file and the software determines how many are first returns, last returns, which points have which classification codes. A lot of the visualization and filter tools don't work unless those statistics have been generated. And what we'll get to is there are tools to convert your data from this three-dimensional point cloud to a surface, say as a raster elevation model. The software doesn't really work directly with the point cloud, at least not yet. So what we'll do today is convert to rasters for analysis. So the first hands-on activity we'll get to is we're going to create an Alias Dataset using using data from Clemson University, or that covers the campus here. So we're going to examine our data both as elevation and then classification and returns, and use some of these visualization tools. So from our data folder here, the using and visualizing LiDAR and GIS folder is an ArcMap document already created for us to work from, this intro to LiDAR _initial. We can go ahead and open that in ArcMap.
While it's loading, I have a question about the intensity property. So is that determined like based on how fast you're flying or something?
The intensity is, so the strength of the returned signal. So if you're measuring something that's very far away, simply distance can affect the intensity, as well as, I don't think the speed of the aircraft really matters, but there's several factors at play. The primary ones are how far away it is, but then also what that reflecting object was like. Yeah, so how bright it was, or how much of that energy it absorbed.
So if you had like a fourth return, it would be less intense than something that only had one return.
Most likely. So if you get this message about hardware acceleration from ArcMap, we want to say no, do not enable hardware acceleration on our computers. And I'm going to go back to my data folder here. I pointed out this folder before, LAS Files. So if we open that, this collection of our first 6 files in here that start with 2011, 319, SC Pickens County, 2011, whatever. These are data that were the Department of Natural Resources contracted people to fly over the entire state of South Carolina in different years to collect airborne LiDAR data. And so these are a subset of the Pickens County data set. So I got these through the NOAA, or National Oceanic and Atmospheric Administration data portal, and downloaded them. And then there's a few other ones here that we'll work with later on. So these first 6 files that all have Pickens County in the name, this is where we're going to start.
Oh, in this set.
There's 12. Okay, well, you should see at least these 6 in that list. Well,
34,
yeah, I've got a list of them here. So, all right. So we can close our business analyst message center here. So here's our imagery base map. We're looking at the Clemson area. We have several data frames already created. I'm going to minimize my data frames here on the left and remove this layer called Business Analyst Network Barriers. All right. If you're going to work with LiDAR data here in ArcMap, we need to turn on a few extensions for everything to work properly. So who remembers where we go to turn on extensions? Scott, you're banned from this, this part.
It's a question.
So yep, from our customize menu, we'll go to extensions, and we need to enable the 3D analyst and the spatial analyst extensions. So check the box for 3D analyst, check the box for spatial analyst, and then click close. Okay. So then next, what I'll do is notice here in Arc Catalog, if you don't have that window open, we can click our button here at the top or from the right of the software. We'll be working out of this home directory. So I'll expand my home directory. Notice we have this Elias Files directory. Go ahead and expand that here in Arc Catalog and see what happens. So we know there's at least 15 data sets in there. But this is just another hint that ArcMap doesn't deal directly with Elias Files. So it doesn't even show them here in the catalog. So what
does that mean? It doesn't deal with them?
It doesn't allow you to add them directly as it would other data sets. Yeah. So what we need to do is create that Alias Dataset that's going to reference those files and allow us to view them. So anybody other than Scott, how do I create a new data set through Arc Catalog?
How do you define a data set?
Any data set.
General tool.
The general way of creating new things using Arc Catalog.
Must be right click.
Right click on what? Right click somewhere. So if I right click on this home, here at the top, we have our new dialog where we can create new shape files, new file geodatabases. Here we want to select new LAS dataset. And it should be added here to your Arc catalog with that terrible name of new LAS dataset. So let's rename it Clemson Campus. All right. So now we have this LAS dataset. It needs to have the LAS files added to it. So let's right click this Clemson Campus LAS dataset and open the properties. And so from our properties dialog, we want to go to the LAS files tab. And this is going to list any of the LAS files that make up that dataset. So what we want to do is click here, add files at the bottom. And then we need to navigate now to that LAS files directory. So from computer here on the left, and then the data to D drive, and find our using and visualizing LiDAR and GIS folder. And then the last files folder within it. And because I guess all of yours are different than mine, we're looking for the following files. What I would do is click first on the one ending in 000034, and then hold Control and click on the one ending in 35, the one ending in 40, 41, 65, and 71.
Looks like you're holding the shift key there.
Holding the control button. So I first clicked on the one ending in 34. hold control, then click on the one ending 35, 40, 41, 65, and 71. And then click open. So now we have our list of LAS files, their name, the version. These were LAS format 1.2. We can see how many points are contained in each file. So anywhere from about 2.9 million to 4.6 million points in each file. And we see a spacing, min, and maximum. Let's click on the statistics tab.
So what does that Z-min, Z-max mean?
That's the minimum and maximum elevation in the data.
And that's like an average point spacing, 0.8?
Yep.
And we're assuming this is in degrees?
In the units of the coordinate system.
Whatever that is.
Whatever that is. Scott's anticipating the next 5 things I'm going to point out as we go.
Well, I know it has to be meters.
Right, so let's go to our statistics tab, and you should see it says 6 files have outdated or no statistics. We wouldn't want to click on calculate. And this just builds another small text file that will be stored in that Alias Files directory. But now we can see information about our data set. We can see how many points were first returns, second, third, fourth, last returns, and the different classification codes in our data. So what classification codes are even present in our data?
Intensity? That we're talking about?
Here in the middle, it says classification codes. So we have about 42% are unassigned. 46% are ground. We also have a few that are noise. Somewhere there's a model key or reserve. This is basically a thinned subset of the data that some algorithms use. Not really important for us to know. We have a few that are water and also some classified as rail.
So what's the implication of the unassigned? That useful for us?
Just that they haven't been determined to be the ground, water, rail, or noise. So it doesn't mean that they're not useful to us necessarily. We just know that they are not the ground.
Treetops.
They could be trees, they could be buildings, they could be other things. Power lines, whatever. So now let's go to our XY coordinate system tab and see what coordinate system our data are in. What do we find? Are they in geographic coordinates or are they in a projected coordinate system? They're projected. How did you know? Because it says projection right underneath it, right? And what's our unit? And again, this is the XY unit. It's in meters. And if we check out our Z coordinate system, it says it's unknown, but we know that it's in meters.
Because it says so.
Because it says so. So these are in a projection. If you download, say, from the USGS, the DNR, or NOAA, you'll often get these things in geographic coordinates. ArcMap doesn't deal well with displaying data in LiDAR data or as Elias files in geographic coordinates. It interprets the latitude and longitude in the 3D displays as true X and Y, and they show up as a thin band. So if you're ever working with data and trying to view it in 3D and you see them display that way, they're probably not projected. But here, these are already set in a UTM projection. So let's click OK, close our properties here, and let's add this Alias dataset to our data frame.
So if you have the data in GCS, and if you convert it to projection, then it's all figures itself out, right?
Yes. So if we click on Clemson campus here in Arc Catalog, drag and drop it into the data frame, what do we see? Squares. Not too interesting yet, right? But what are each of these red squares representing? Yeah, these are the extents of each of these individual LAS files. And here in our table of contents, we see there's a rainbow color scale assigned to our points. It's showing the elevation, and it's also telling me the data percentage it's displaying right now is 0. So go ahead and start zooming in. And once you get to about 1 to 8,000 scale, the points should start displaying.
So that scale factor, is that something ArcGIS is doing because it's saying this is an Alias Dataset, I want to show all this stuff until I scale it?
Yeah, the software doesn't look, it tries to restrict the number of points it will display to try and keep it from bogging down your machine. So, so now I'm zoomed into 1 to 6,000 scale, and it's telling me it's showing about 7% of my total data. But go ahead and pan around the data set here, take a look at it, zoom in, zoom out, get familiar with it, and tell me any observations you have about the data. Where there are points, where there aren't points. Any features you notice?
So here we're looking at the scanner.
Yeah. So if you zoom in very close, 1 to 300, 1 to 500 or something, you kind of notice this orientation of the points in this sort of southwest northeast line. So I would infer that the plane was either flying to the northwest or to the southeast. Can't really tell, but the scanner was rotating and scanning along these lines here. So where don't we have data? Anything stand out?
There's a problem with water, right? Like the pond over here.
Yeah, the reflection pond or Lake Hartwell. We're not really getting points over the water. The water surface is continuously moving and then scattering that energy different ways with the scanner, so we don't really get a good return from it. So how dense is our data? What do you guys feel like the average point spacing was or is? As if you zoom in closely, we can use the measure tool. Wait for my display to catch up here. You can see there's not a uniform spacing between the points. If I use my measure tool here, I see some points are 13 centimeters apart, 50 centimeters. Between these two, it's about 1.2 meters, 1.8, 0.45. So what do you feel like the average point spacing is just intuitively?
A meter. A little less than
A meter? Right, if we open our properties again, from our catalog, I can find my mouse here. If we right click, open those properties, again, going to that Alias Files tab, here was our point spacing, which was at minimum, on average, 64 centimeters up to just 77 centimeters. So on average, we have more than 1 point per meter squared. So a pretty dense data set.
So if you're going faster, you'll end up with a more sparse data set. Right?
Yeah, if you fly the plane faster, all other things being equal.
It's northeast, southwest. Is that kind of a set how fast your scanner is rotating? Right, because if you're flying faster, they will be the direction you're going more widely sped. But right, can you set the scanner to rotate at a speed?
Yes, you can adjust that as well. So there's also an angular step and an angular speed, basically how often you're going to measure as it rotates and how fast you'd be rotating. So we can change a few settings here in ArcMap to change the number of points being displayed. If we now go to our table of contents, right click on that data set and open the layer properties. We have our symbology tab here where we can change the number of classes, the color ramp. It tells us we're using or displaying the elevation. If there were other properties, say the RGB values or the color, they would also show up in this list. So these data don't have any color information. But if they did, we could show it and that would be in our list here. Let's click on the display tab. Here we have some rendering preferences. So the default point limit when we first opened the software was 800,000. I think the maximum is 5 million. So if you type 5 million in here and then click apply, it tells you I exceeded the limit of 5 million. It changed it to 5 million. But here, the maximum number of points it will now show has increased a bit. Say from 7% of my data up to 21%. There's also a point density. And so try adjusting this slider. If you go all the way to coarse on the left and then click apply, notice it's not showing as many points in your data, but if I close my layer properties and now move place to place, it loads it, it draws it much faster.
That's
just for displaying, not actually changing the data. If I go all the way up to fine, say 10 points per centimeter on screen, click OK. Now I see I'm getting 36% of my data, the highest yet, but it takes longer for my points to draw, especially as I zoom out.
So if you go to the DNR website, you can download the whole LiDAR for a county, one fell swoop.
Mm-hmm.
And does that have, is that lower, or farther point count or point what's the term we use?
Point spacing or point density.
Is that the same or is it a coarser? This is the whole freaking county.
So you'll download them as a set of files, I think.
No, you get one whole county, like several hundred megabytes.
If it's only several, I haven't seen that. If it's only several hundred megabytes, it would have to be a much lower resolution.
Okay, so you go to the NOAA site, you get these little individual tiles.
Right. The USGS Earth Explorer will provide the same data. All right, so I'm going to close my layer properties here. I'm going, before I do, I'm going to change back to about 4 points per centimeter just so it draws a little faster for me. So the next thing I want to show you is the Alias Dataset toolbar. So if we want to add a toolbar, we can go to our Customize menu to Toolbars, scroll down and find the Alias Dataset. So I'm going to drag and drop and dock it up here in the center. Maybe remove a few other toolbars here that I don't need.
Sorry, where did you get the Elias toolbar?
So I can go to customize toolbars, or I can right click up here in this gray space to turn toolbars on and off. So this toolbar won't work unless you have the 3D Analyst extension turned on. So if you leave today, try this on your own. Remember, we need to enable these extensions for it to work. So what will show up here in the toolbar is the active Alias Dataset layer that you're going to visualize or filter. So if you have multiple Alias datasets in the data frame, they would show up in this drop-down list. Right next to that, just to the right, is this icon with some points here. That means we're displaying or viewing our data as points, and the default is by elevation. So if you click this drop-down, we can view them by classification. So go ahead and try that. And then what do you notice about the data? What are the two classes that stand out immediately? Yep, ground and unassigned, which we know are over 90-something% of our data here. What others do we have in the data, though, and where are they? So there are some labeled as water. If I go next to the old pond here, I see some labeled as noise, and then I also see some along the banks marked as rail. So that's kind of interesting. I'm not sure how they designated those are rail.
It's catching the road.
So we can also view our data from this dropdown then as returns. So showing these by that return number. So whether they are first return, second, third, or fourth.
So what that classification scale is telling us is that it's an unclassified, it's an they call it unsupervised classification. They just slap it on. Nobody really checks it.
That's the default. So here they haven't differentiated as ground, water, rail, or noise. It's just not any of those.
What caused it, like in the upper part of that neck there, in the water, why are there points in there but not points in the other part of the water?
It's like here versus here?
No, like,
or
yeah, like where you just were, there are points in the water that are making water, and then a lot of water that doesn't have water.
You know,
something to do with the angle of the.
Maybe, I'm not exactly sure why on that particular day at this location they would have had some reflections here, but not right here. Whether there was wind moving across the water or like you're saying, a broad angle or something, I'm not really sure.
Just get down there, it seems like that's
pretty flat,
like
calm. Oh yeah.
Over the creek and actual water. Right, because that's the sewer treatment plant, right?
This, these I think are now practice fields.
Oh, okay, not too far down. Yeah.
Stephen, did you have a question?
Yeah, I was just curious, the points classified as noise, are those just bad points pretty much? Or?
Yeah, generally these would be a point that have some elevation that's very far off of their surroundings. So maybe there was part of a cloud, some atmospheric thing, or it just got a reflection from somewhere else, some scattered energy that it thought was that far away, but it, not consistent with its neighbors. So as you view the data, where do we have things other than first returns, say second, third, and fourth returns.
Leave the tree.
Yeah, so if I switch my Alias Dataset on and off here, I see a pretty clear pattern with lots of second, third, and fourth returns where I have lots of trees. Not so many where I don't have trees. All right. So now I'm going to switch my display here back to elevation. And next I'm going to click here to the right of that. There's another option that says elevation, and here it's going to connect my points as a surface and then display them on the fly here. So any settings I make on that point density that I adjusted before would be reflected here. So notice my data percentage is about 11.5%. If I bump up my point density to 10, I'll get a more detailed display here. So now almost 30% of my data. But now it really starts to look more like it's a little easier to interpret things like buildings, the ground surface, roads, and all of the other features in this display. And if we click that drop down again, we can visualize on the fly both elevation, we could do aspect. So which compass direction each of these surfaces is facing. We can also view the slope. And we can do on-the-fly contouring of the data. So I'll switch back to my elevation surface here. And notice then to the right of that is this filters drop down. So here we can, the default is to show all the points. If we click ground, that's going to remove any points that haven't been classified as the ground surface. There's also a non-ground, or we can try our first return. And if I switch that back from my surface to my point display and go to elevation, notice as I go to my filter to ground, it's now removing any points from the display that didn't come from that ground surface or haven't been classified as coming from the ground surface.
What was that last thing you did? Sorry.
So I set my filter to ground and then switch back to my point display here. So any filters I make to my data here are going to be honored by any processing tools that run on this Alias dataset. They're also honored by our display here. So again, if I switch back to this elevation or the surface display and now go to the contour, it's going to contour just those ground elevation points. So I see something that looks a little more like I would expect.
You said surface?
Yep, so here next to point to the surface display, I selected contour. So now it's contouring just those ground classified points. All right, so I'm going to switch back to my point display now. And I'll set my filter to all. So I'm going to turn off any filtering and show all of my points again. If I continue down the Alias Dataset toolbar, near the right side is this Alias Dataset profile view. So what this is going to allow us to do is draw a line through our, somewhere here on the map, and then view a cross section or a profile of those points. So what I want you to do is put Death Valley Stadium somewhere in the center of your map here. And then let's try this LAS Dataset profile view. I'll click that button. Notice my cursor becomes this crosshair. I'm going to draw a line, clicking first here on the north side of the stadium, then down through to the south side of the stadium. And once I do that, now notice it's going to draw a box. And so this sets the width, or how many points I want to show in that profile, with some maximum of points about this far out. So you can make it skinnier or wider, it's up to you here. But now I'll click, and I should open this profile view so I can see. Here's the edge of the stadium. Here's the field, the different tiers or decks.
How did you get that to open?
So I
create the box part, right?
Yep. So I first clicked above and then below the stadium, set my box width and clicked again. No.
You have to be touching the box.
It's telling you not right there, it's too wide. So just retract the box.
Oh. Okay.
So there's some other tools available to us here. You can see we can zoom in and out in our profile view. We can pan around and move our profile. We can identify specific points or grab information about them. Say their elevation, their coordinates. We can also measure things. If we want to know how tall features are or how far apart specific features are, we can measure those here. So how high, or what's the elevation change from the football field down here, standing on the field, to the top of the stadium? So I'll click my measure tool, click here on the stadium, click a point up here. What's that elevation change you get? I got a difference of about 55 meters between the two. Something we can also do, we can edit classification codes of our points from the profile view. So we can select points using the selection tools, and then we can actually change classification codes of our data. So let's give that a try. So I'm going to close my profile view.
So you may want to save your program.
Did it? Uh-oh. Well, I'll wait a minute for you to open it again. We haven't really lost anything, since all we have to do is drag our Alias dataset back into the.
Yeah, it seems like it's that profile view a little different measuring things.
Really? How many? We had 2 crashes. Anybody else have a crash? No.
I was trying to do 2 minutes. I wanted to do 1.
All right. So as we wait for those to open again, let's go to a building location here. So let's reclassify these points around Cooper Library, which if I view these points by their class code, I see this gray area that tells me that these were unassigned. So if I want to classify and tag this as a building, we can do that through our profile view. So I'll click here on my profile view, draw a box.
Some algorithm that says this is an anomalous structure. I'm not going to classify it, right? Because it's not fitting in with the ground level around it or something.
Yeah. So what these algorithms generally do is to classify ground from non-ground. It's going to identify continuous planar surfaces that have a fairly low slope. And so it will do it different ways. The last tools that we have on these machines fit a tin surface through the points. And
what? A tin surface?
Yep. And then any of those areas that are fairly continuous, low slope, and we tag those as ground and leave everything else as unclassified.
So does this sometimes have a problem in like places out west where you have big towers and spires and cliffs?
Yeah. So the next processing step, say to differentiate vegetation and buildings, would be after it's determined these flat areas that are ground, it's going to try and determine if there are other planar things higher than the ground. It might be roofs of buildings or steeper things, say vegetation or trees. So these are just automated algorithms that will attempt to classify these. We generally have to go in and do some quality control on our data here, where we can always go through here and manually classify those points. So is your ArcMap back open again?
Still there? Saved it somehow? Does it have an auto save? Or is it just there?
I don't think there's an auto save.
I didn't save it. I mean, I just moved it on. I never saved it. Saved it.
Oh, yeah, the data set once we created it. It's not a property.
Okay. Data set.
Yeah.
Oh, I get it.
That's what I'm saying. We haven't really lost anything.
I see what you're saying.
Okay. So let's find Cooper Library here. Let me find my mouse. I'm going to zoom in around Cooper Library just south of that reflection pond. Grab my profile view. And I'm going to draw that profile through the building here. And then adjust the width of my box. So I'm essentially just grabbing Cooper Library without much beyond it. So I can see these points here just off the ground. That looks like our balcony railing along here. We have our roof. We have that structure, whatever it is, that plus sign up on the roof. And notice as I move my mouse back and forth through the profile, it also shows this cursor moving in the map, showing me where I am in the profile. But what we want to do here, what?
What is our filter?
Oh, I have it on classification. So next we want to click on these selection tools here. So I'm just going to click where it says, rather than select by envelope, select by polygon. So we're going to click and draw a box around Cooper Library's points. So here where it says select points by polygon, now I'll click and start defining this polygon here around Cooper Library, stopping just above the ground surface here. coming back across. And then I'll enclose the rest of the library points. And then double click. And they'll all show up in this selection color here in blue.
But it only does it in the profile?
Only in the profile, yeah.
What are we doing?
We're going to reclassify these points. So if we click here on the edit, this gives us an easy dialog where we can click a classification code number or select from the dropdown. It's telling us that these have been unassigned. Here in my dropdown, I see all the potential classification codes we could give it. So I'm going to select number 6, building. Then click apply in the lower left corner. And it's telling me we may not see a change. That's fine. We can click dismiss, dismiss. And then if I close my profile here and switch my view from classification back to elevation and then back to class. Oh. Let's remove them. I haven't tried this one beforehand, so it would show up as building points.
So I'm in have a cross section up. So what tool would you use in the profile?
Yep. So for my cross section, once I selected, I clicked on edit.
And then you did what?
And then I clicked apply.
First, you have to draw your thing around it, which you did now.
Oh, sure. So here, the selection, I did a select by polygon. And then clicked and drew a box around it. So any guesses why our points aren't showing up? Yeah, the symbology doesn't know how to show them, but what did we do when we first created this data set? We added Elias files to it, and then what did we do with them? Not classified them, but
Displayed them.
we read the statistics. And so if we open once we've updated our data in the profile view, let's close our profile view. Right click that Clemson campus LAS dataset and open the properties. And if we go to the statistics tab, it's telling us one file has outdated statistics. So it knows there's been some fundamental change to our data. Click on update. And now it's updated and shows that, at least in mine, yours may be slightly different, 0.03% of my data now have a building classification code. I may need to remove this data set from my data frame or add it again to see those points. So if I drag and drop it from the data frame, turn off this first instance, and now go to my classification display, I also need to go to my drop-down, my Alias Dataset toolbar, select the second instance, and go to classification. Now I see them show up in pink. They've been classified as a building. So this is really the only interactive way in ArcGIS you can go and change any classification codes. I'll switch back to my elevation display for my points. And then You've probably already opened the Alias Dataset 3D view, but if you haven't already, go ahead and click that button right here at the end of the toolbar. And this should open another window that gives you a view of those points in 3D that we can click and rotate. We can zoom in and out using the mouse here. We can also measure points. And here at the top where it has this number 1, we can adjust the vertical exaggeration as well. So the default is 1. If we want to, say, magnify those elevation differences by a factor of 2 or more, we can adjust that there. And this 3D view will honor any filters you make from the Alias Dataset toolbar. Say if I just want to view those ground points, it's going to show me just those ground points. And I can also create that surface, and then from my Alias Dataset 3D view, it will show me my data as a surface.
So it's supposed to be updating your 3D when you do this? Or you have to close it?
You have to close the 3D view and then open it again. Yep. So if I filter my first return surface, I can see my buildings. And if I view them, I have a lot of exaggeration here. This is my digital surface model now of campus. So I can zoom out here, get a broader view. Excuse me. All right. Well, feel free to experiment for a few minutes. We can also take a break right now for 12 minutes or so. Come back at 35 after. Feel free to use the restroom, grab a coffee, play around with the 2D and 3D views. We'll pick up again in a few minutes. All right, so how's everyone feeling about LiDAR so far? It's awesome.
A lot of the data sets are just out there. Like, if you wanted to do a data set of an agricultural area in Saluda County, find that someplace.
Yeah, South Carolina is pretty spoiled that the DNR had the state flown. I mean,
Okay.
the data go back over 10 years in some counties, but pretty much everywhere has been flown at least once. Other places are not so lucky.
Right.
Finding the tiles, I've actually done that. For the Clemson area, that's interesting process. What you did, you showed us, that's a little bit
Yeah.
It's about an hour.
Yeah, there's some work behind the scenes to get the data ready for you all to just throw in the map here.
Yeah, I figured out how to get the data, and I just didn't know what tools they built
To get from. Mhm. All right. So what we're going to work on then next is, so we brought our LiDAR data into GIS and seen different ways of filtering and visualizing. The next thing we're going to do is use the Alias Dataset to raster tool. So this is a tool that will take a 3D point cloud and it's going to interpolate it and convert those points to a two-dimensional grid. So we're going to do that to create this an elevation model using just the ground classified point. So this elevation model will represent bare earth elevations, and then a digital surface model that will include things like vegetation and buildings. So we'll start there. So if we go back to ArcMap here, what we need to do first is, I'm going to play with my display here, just go back to viewing it as points. And let's first use this Alias Dataset to raster tool to get that bare earth elevation model. So what we want to do is filter using the Alias Dataset toolbar here and just keep ground classified points. So we'll set our ground filter. So next we want to find the Alias Dataset to raster tool. I'm going to use the search window or hit Control F on my keyboard or click here at the top to search. And this is Alias Dataset to raster. Did not match any documents. Yes. That's all right. We're just going to have to open Arc Toolbox and click a few more buttons. So I'll click here, open my toolbox, make a note to myself that my image has an error in it.
I think you just forgot an A in your search.
Oh, yeah, okay. I just can't type today. That's all right. I'll show you where it lives in the Arc Toolbox for your own knowledge. I just have to wait for the toolbox to open here. So from Arc Toolbox, from the conversion tool set, and then to raster tool set. The Alias Dataset to raster tool is in there. If I double click to open it, it's showing up on a monitor I'm not projecting. Give me 1 second. What I'm also going to do is remove, I had 2 instances of that Clemson campus Alias Dataset, the original one, and then the one with the updated statistics. I'm going to remove the original one here. I'll just right click on it, remove from the data frame. I had added the Clemson campus Alias dataset twice. After I had recalculated the statistics, I removed the original one. All right. So here's my Alias dataset to raster tool. I've got the tool help shown here on the right. So what this is going to do is lay out a grid over our LiDAR point cloud with a cell size that we define, and then it's going to take either the elevation values, the RGB values, or the intensity values of those points and assign them to a cell. So what we will first specify is our input Alias dataset. So in my dropdown here, I'm going to grab clemsoncampus.lasd. And our output raster, I'm going to browse to my home folder here at the top. And I'm going to save my output in LiDAR results geodatabase. And I'm going to call it Clemson BEM. And then save. So here where it says value field, this is where we can select what we're trying to assign to a raster. So the default option is elevation, which is what we want. The interpolation type here, we're going to use the binning method, which means it's going to combine points within each one of these cells. We can do an average, inverse distance weighting of points, take the maximum, minimum, or nearest value. We'll take an average. And if there are no points within a cell, we're going to fill those. We'll leave the default, which is take a linear interpolation of surrounding cells. Oops. So binning, we'll leave the defaults average and linear. The output data type, we could save either an integer raster or a floating point raster. We can leave this as floating point. Our cell size and the sampling value is where we're going to set up the size of each cell in our grid. So let's do a 1 meter resolution grid. I'll type a 1 for my sampling value.
So that means we're going to sample.
So we're going to create a grid with 1 meter cell size. That's our sampling value. So then we can click OK. I think my progress is being shown on this other monitor. Yep. So once it's completed, I can close this window. I'm going to turn off my LAS dataset in the table of contents and then take a look at this raster. How does it look? I had to restart? Okay.
So it was done before, all CCTV screen, the map should be stop.
Just
Yeah.
Okay.
you go to the catalog, and hopefully, I have that Clemson campus. Alias Dataset. Let's add our Alias Dataset toolbar. And then we define that Alias Dataset to raster. That's what lots of companies do working on. So you hit Control F for the search wizard. Never had to do that. So here. It's Dataset to raster. Here, I call it Clemson. And here, I just scroll down. So we did elevation. Okay. I left the walls. Right. And then scroll down. And we set the cell size for the as. It'll go from 0 to 100 like instantly. There it goes. Okay. Thanks.
What do you think about our elevation data set here? Does it look okay? For those of you who work with elevation data a lot, any observations?
That's got some weird things in it. That's some man-made stuff, but that's to be expected from LiDAR. Right?
Like which ones are you referring to?
Squares.
The squares, right? So we had a building here, and we had to do a linear interpolation all the way across here so that we wouldn't have a gap in our data set. All right. So now let's also construct that digital surface model. We're going to run our Alias Dataset to raster tool again. I'm going to turn on my Alias Dataset just to make sure I set my filter correctly. So if it's a digital surface model, I want to set my filter to be the first returns.
So what we show is going to influence the VLM?
Yes, any filters I apply through the toolbar are honored by that geoprocessing tool.
So we had it on.
We had it on ground before.
Now we're going to go to first return.
Yep, we'll set it to first return.
So now we want to see trees.
Yes, so trees, buildings, everything. So let's search for my LAS dataset to raster tool again. From the conversion toolbox here. So our input LAS dataset will be Clemson campus. And I'll save my output raster in that results geodatabase. So I'm going to browse to my home folder, go to LiDAR results geodatabase, and I'll call this Clemson DSM. I'm going to leave these defaults again for average, linear, and binning.
So if someone's already taken that.
And I'll set my sampling value to 1. And then click OK. I can run the tool. And once that's finished, I'll turn off my Alias Dataset and view my output results here.
So it's weird to get lower values.
Yeah, I think there's a few noisy points in there. There's also this very, very high point right here with nothing else around that kind of drags it in that location. But here we can see in our output raster, we have elevations from our trees, from our buildings, as well as that ground surface. Any other observations, comments about it? All right.
Kind of like looking at the Milky Way.
Like all these little constellations of stars and things. Yeah, so now we have some very high resolution elevation data sets that we can use for all sorts of other applications here in GIS. This Alias Dataset to raster tool is a really convenient way of converting from a point cloud to this format. So what I have are a variety of different applications that we can go through depending on interest. One possibility is we can create a very simple 3D scene just using polygons representing building footprints on data and our elevation surfaces. So I can quickly introduce you to ArcScene, which is the 3D GIS counterpart to ArcMap. Basically pull in our elevation data and use our LiDAR to get building elevations. And so just do a simple visualization of buildings getting their height attribute information from the LiDAR data. We're going to skip this classifying a raw LAS file for today. I have an application for locating solar panel arrays, basically doing a solar radiation calculation. A cell tower viewshed analysis. So a viewshed is the geographic area that's visible from either a point or a set of points or a line or polygon. So how that might apply to locating a cell tower here on campus. There's a canopy height determination. So looking at a forested region here, if we want to quantify the heights of trees within some area, how do we do that? And also try to identify habitat for my favorite fictional animal, the Clemson tiger bird here, which we know has very peculiar nesting habits. And so here we can also reclassify our LAS data set based on height information if we want to tag things that say low, medium, or high vegetation. And then there's also a watershed delineation here where we can calculate a high resolution elevation data set and delineate all the basins within that region to try to determine if there's nitrogen runoff coming from this farm into what we think is the watershed for Pristine Creek here. Just a simple example. So I don't think we'll have time for all of them, which is always the case. I'm a little too ambitious here. So how many would be interested in getting building heights and viewing this as a 3D scene? You can vote for more than one too. So we got like 4 people, okay. How many for calculating solar radiation across building rooftops? None? How about a view shed analysis? So identifying areas visible from a particular location. Justin, all right. How many for canopy height? Got 4 again. And watershed delineation? 2. Okay.
So have you written tutorials for all this?
Yep, they're all in here in the PDF that's in that folder.
That's
Okay, so the 3D scene and the canopy height had the most votes, so we'll start there. Right. Yeah, all of these are in that tutorial document, which is in that using and visualizing LiDAR and GIS folder.
PDF?
Yep.
Okay.
It's the one title of the handout. So this will have, we'll walk through all of these if you'd like to try them on your own later. Okay, so what we're going to do for, if we want to get these building heights, we're going to use a few tools and some joins to get the elevation or height of every building using our surface model that we just created here. So let's right click on our elevation models data frame and activate it. And this is pretty much what we were looking at before, insufficient memory for the base map. Okay. That's all right. I have polygons for building footprints here around campus. And if I open my attribute table for those buildings, whoops, not my properties. If I open my attribute table, I can see the information I have about them, a building name, potentially their address number, construction year, and an address. What we're going to do is get the height of each one of these buildings or grab the elevation and append that as an attribute back to the polygon here. So we're going to first convert these building footprints to a single point of one representative location for each building. And then use a tool called Add Surface Information. That's going to take the points representing the center of each building and grab the elevation from our DSM that we calculated. And then we'll join that information back to the table. And then bring that into ArcScene and use it to visualize these features in 3D. Question?
Did someone have to go in and like draw out all of these polygons?
The source of these is actually the University Planning and Design Office, the ones responsible for maintaining the primary database of spatial information for campus. So if somebody did draw these, they generally come from the engineering and CAD drawings. Okay, so what I'm going to do is I'm going to drag and drop my DSM from our catalog into the data frame here. So I need to go to my results geodatabase and grab that Clemson DSM and put it into the data frame. Right. And I'll close my attribute table here. The first tool we're going to run is called Feature to Point. And so again, this is going to allow us to get one representative location for each one of these building polygons. So I'll go to my search dialog, hit Control F on my keyboard. Yep, see you, Scott. Don't forget your jacket. Jacket?
Oh, yes.
Yeah, you might want that.
Which one did you drag in?
Oh, the DSM. So from my results geodatabase, Clemson DSM.
Yeah. I put it somewhere else. Campus, yes.
Did we save it?
Well, you can use campus. Oh.
Yours is from an earlier version of the workshop out.
Okay.
So you can basically edit this, but the process will be exactly.
All right.
All right. Okay, so from my search window, I'm going to search for feature to point. It shows up down here from the feature management or data management toolbox. And my input features are going to be my building footprint, so the Clemson University buildings 2011. My output feature class, I'm going to save in my results geodatabase. So I'll browse, go to look in, home. It's not there. I'll go to my default geodatabase, go up one level. And here's my LiDAR results geodatabase. And I'm going to call this buildings _ points. And then click save. And then run the tool, click OK to run it. So what it's done is it's placed a point at the centroid of all of these polygons here. Everybody with me? All right. So the next thing we'll do is search for the Add Surface Information tool. So from my search window, search for Add Surface Information, which is from the 3D Analyst tool set.
What kind of, this is the like the points, if it's like 3 buildings averaged in between, and the points actually like on the ground, like in the thought center or something.
Some of these. Yeah, so this is just going to be an approximation of it. So if we have multi-part polygons, which some of them are, yeah, it's taking the centroid of all of those polygons here. So yeah, this is more for just a visualization exercise. So our Add Surface Information tool from our 3D Analyst tool set. Our feature class is going to be our buildings points. And our input surface would be that Clemson DSM. And we only have one option for the output property. So check the box next to that letter Z. So again, what it's going to do is for each of these points, it's going to look at that DSM cell underlying that point, and it's going to grab that elevation value, and it's going to append it to the attributes in a field called Z. And that's going to represent the elevation at the top of that building. So we can accept all of the default values and click OK. And now if I open the attribute table, I see that Z field. So here's that elevation of the buildings themselves, at least for this one particular point. So our last step is we need to join this information from this table back to our building footprints. So here's a review from several weeks ago now. If I want to join this Z attribute from this table, or join all of these attributes for that matter, how am I going to do it? Louder? What do I need to do?
The polygon layer.
Right click the polygon layer, okay. Go to joins and relates, join, all right. Yep, so we can join attributes from a table. For section 2, we only have one other table in the data frame, which is building points. If we go to option 3, choose the field from the table, there's this new attribute called original FID. That is the FID of the polygon that it's based on. So if I select object ID for number 1, that will be the same value that shows up in original FID here. So just to show you, you don't have to close yours. I'll just show you again what we're doing. Each one of my polygons have this object ID that's automatically assigned to it. When we converted these to points, it gives us the FID, or feature ID, or object ID that are sort of synonymous of the source polygon here. So we're going to link this original FID field to the object ID here. So let me set that up again. Joins object ID for number 1, original FID here. My join options, I'll keep all records and validate the join. It says 261 of 261 matched, which is good. So then I'll click OK. And I see this joined information. And there's that Z field.
It has to create an index for you. I'm trying to create an index. One field in one table, not index. No.
Yeah, click OK. So what do we know about tabular joins in our data? What I need to do is I'm going to bring this polygon layer out of ArcMap, and I'm going to open it in a new software, ArcC. So what do we know about tabular joins in ArcMap? Does this building polygon data set have this join information forever? No, right? If I close ArcMap, that join will go away. So what we need to do is export a copy of our data, and it's going to preserve that join and give us all those attributes. So what we need to do is go to our Clemson University buildings footprints here in the table of contents, right click on them and go to data and export data. We'll export all features, use the same coordinate system as the source data, and we'll save our output in that LiDAR results geodatabase. So I'll click my browse button, look in my home folder for the LiDAR results geodatabase, and I'll call this buildings _Z. And then click save and OK. And I don't need to add it to the map as a layer. So I'm going to save my map document for now, save these changes. And what we want to do is open ArcScene. So go to the Start menu, All Programs, ArcGIS, Folder, and open ArcScene. So this will be a very quick introduction to the software, but this is the 3D counterpart to ArcMap. So rather than building a two-dimensional map, you're going to create a three-dimensional scene. So we can visualize our geospatial data in 3D, as well as perform a lot of 3D analysis through this program. And we're just going to add two data sets to our scene. We'll add our digital surface model elevation data set and then these buildings. And so we're going to first add them as polygons that are going to float on our elevation surface. And we'll see what that means. And then we're going to extrude these polygons, which will basically turn a square into a box. And we're going to use that elevation data to do so. So here under new scenes, we can just click blank scene, click OK. I think I have to sneeze. Nope. I know. Love that feeling. Okay, so we want to expand our ARC catalog here. We'll need to connect to a folder. Right, need to connect to that using and visualizing LiDAR and GIS folder. So right click my folder connections, connect to a folder, expand my computer at D data 2 drive, connect to using visualizing LiDAR and GIS. Click OK. And then I'll expand that folder in my folder connections. Let's first add our DEM just to start. Okay, so we'll go to my LiDAR results geodatabase here. And I'm going to drag and drop my Clemson DEM now into my scene. So it's going to show up here not as a flat map, but in this 3D perspective view. And if you click and drag the mouse, you can rotate this thing around here, right? Because we're now viewing it as a three-dimensional scene. So next, let's add, I'll go to the catalog and add those buildings with that Z information. So here I have this feature class buildings Z. In my LiDAR results geodatabase, I'll drag and drop into my scene. So now I see all these footprints, and they're basically now these flat objects. Is everybody there? Good. All right. So what we want to play with here to improve our visualization is adjust the height information or the way the software is going to display these in 3D. So if you have a raster surface, like our elevation model here that actually represents elevation, we're going to assign its elevation values to be whatever its value is in the raster. So in terms of the software, we're going to tell it to float on itself. So it's going to use the elevation values in the grid to put it up at its true elevation here. Does that make sense? If not, it will in a second. So if we go to our table of contents, right-click our Clemson DEM and open the properties. We can change the symbology like we can in ArcMap as well as lots of other stuff, but it's this base heights tab. And this is where we can customize our 3D display. So the most simple things we can do, I'll just point out here at the bottom, I'll apply a layer offset. So just shift this thing up or down, some set number of meters. There's this option, elevation from features. So if you have features, things like points, lines, or polygons, you can use an attribute to give them an elevation value. Or the one we're going to use is here at the top, elevation from a surface. So if we click this radio button next to floating on a custom surface, we can use elevation information from a raster to draw this thing in 3D. And so we're going to set it floating on a custom surface, and our surface is going to be Clemson DEM. So it'll be floating on itself. So if we click apply, and then OK, and then view the results here, now we have our DEM using its own elevation values and showing in 3D. And our buildings are still at 0 in terms of elevation. And if you want to, you can adjust the vertical exaggeration of your scene, or basically magnify our vertical axis here. So if I right click on my scene layers, data frame here, and open the scene properties, there's this option for vertical exaggeration. Just click it up, say to 2, and then apply. And this will exaggerate or magnify those differences in elevation, so we can see changes in topography a little bit easier. So now if we want to get our polygons, our buildings, up here on our surface, let's right-click our building Z layer in the table of contents and go to the properties and then the base heights tab. Right, so if we say that these are floating on a custom surface, we can do that same option here. We can set these to float on our Clemson DEM. So go ahead and click OK and take a look at what that looks like. It's just draping those polygons over that elevation surface. So in the display, it looks a little weird, especially say here at Strom Thurman Institute, because it's trying to draw this polygon at the exact same elevation as our raster surface. Is everybody there? All right. So now let's go and open our base heights tab again for our buildings. And actually, now let's click where it says extrusion, the extrusion tab. So if we check this box, extrude features in the layer, extrusion turns points into vertical lines, lines into walls, and polygons into blocks. Let's check that box. And there's a few ways we can apply extrusion here. We can enter a value, say extrude everything by the same value. So let's just type 20 in our box here and click apply. So if I view the result, what it's doing is it's applying extrusion by adding it to each feature's minimum height. So it's saying what's the lowest height from where it's floating on the surface, and then add 20 to that. So we can play around with these options a little bit. We can apply extrusion by adding it to each feature's base height. So let's select that and then click apply. And we get something that's fairly similar. But I'm trying to find an example of the difference here. So if we see this particular building where it spans some change in topography, we see that it's now extruding not to a flat surface, but the top is a curved surface, because that base height changes underneath the polygon. Whereas before, adding it to each feature's minimum height, it extrudes out to a flat top. Adding it to each feature's maximum height will also give you a flat top. But now we're starting from the highest point in that polygon. And if we use it as a value that features are extruded to, this one will look a little crazy, but if we click apply, and then look underneath, we've set it to extrude to 20 meters of elevation, which is actually 200 meters or so below where our building polygons are. So what I'm going to do then is go to my extrusion tab, and rather than use a set value, I'm going to set an expression using this calculator. So if I click this calculator button, we're going to extrude using that Z attribute. Click OK. And then let's try using it as a value features are extruded to. So now I can see things like those residence halls, the high rises, stand out above the surrounding elevation. I think that was the Clemson house up on the hill that no longer stands but is in our data. And you can do things like change the color of these polygons, these extruded polygons. We could change the color of our topography here. And we can do all sorts of cool stuff to visualize our data here in 3D. What do you think? Kind of cool? Did you know that ArcGIS could do stuff in 3D? Yeah, it's pretty neat. There's a lot of different use cases and possibilities here. The newest version of the software, ArcGIS Pro, has 2D and 3D capabilities built into the same program. We're going to start switching all our workshop materials over to that Pro software probably this summer, and then start teaching it in the fall. ArcMap and ArcGIS, ArcScene, and all these softwares are not going to be developed by the company anymore. The next version that comes out is going to be the final one, they've said. So in the next several years, they're just not going to support it. And they're going to push everybody to this new software. So we're going to start teaching that. So anyway, ArcScene, this is the 3D counterpart to ArcMap here. So just to give you an example of how we can grab three-dimensional information in a GIS from our LiDAR data. Questions, comments? All right. Then let's continue on in our examples here. So I think the next highest number of votes was for canopy height determination. So canopy height, this is the height to the top of the vegetation here in a forest. If we have LiDAR data, we can create that elevation model or representing the ground surface, and then also filter out, create a DSM representing the heights of trees. And if we subtract those two rasters, then what we'll get is a raster of height in some area. So if we wanted to know canopy heights and save that as a grid, this is the way we're going to do it. We'll first create a DEM and a DSM, and then subtract the DEM from the DSM. So here's my sample scenario. Like I said, our Clemson tigerbird, we know, likes to nest in very peculiar areas. Here, we're trying to isolate trees that are fairly small, 5 to 10 meters in height, from this forest tract down in the experimental forest. So we want to identify those areas where trees are 5 to 10 meters high. So what we'll do is calculate or create a DEM and DSM and subtract the two, and then we can symbolize our data to highlight those areas of vegetation And there's also a tool where we can reclassify. So we did this example of manually reclassifying points. We can also use a classify LAS by height tool and specify that trees of a certain height are going to be considered low, medium, or high vegetation. And if we determine that one of those classes is 5 to 10 meters, or we specify that it's 5 to 10 meters, we can then filter our points using that classification code. So it's kind of two ways of approaching the same problem that we can try. So let's switch back to ArcMap here. I'll close my attribute table from before. I'll minimize my elevation models data frame and expand and activate my canopy height data frame. And it's probably going to tell me it has insufficient memory again, but we'll see. Anytime now, software. Activate. What if I remove the base map? Oh. See, I'm going to close ArcScene here. Ah, there we go. Add my base map back. I'm sure it was one of these. Is anybody else's being, oh, and it crashed. Is anybody else's being as finicky as mine? Or does everybody see something in that data frame? All right, give me a minute here to open my map again. So are you able to zoom in on that Alias dataset that's in there and see points and everything? Okay. So we have our Clemson Forest Alias dataset. It just has two of these tiles that were also from NOAA, just like we were looking at over at campus. So what we want to do, again, we want to create a DEM and a DSM from those. So if you remember how and feel like you're confident enough to do it on your own, go ahead and try and construct that DEM and DSM. And we will create them with, let's see, 1 meter resolution. Turn off my hardware acceleration. Or if somebody thinks they can demonstrate for everybody, once this thing opens. Anybody want to volunteer? Show us how it's done. No. All right. I tried. Okay. Move, and mine are broken. So let me fix this. Clemson Forest, last files, 6433, Forest. So I think I copied a different folder to my own computer here. Are you guys the remote participants? Did that Alias Dataset work okay for you? Okay. So if we want to make a DEM out of this Clemson Forest Alias Dataset, what's our first step? We want just the ground elevations, right? So I'll go to my Alias Dataset toolbar, and I need to make sure I select the right dataset. So I'm not going to work with this Clemson Forest reclass. We'll get to that one later. I want to select Clemson Forest.LASD. Go to my filters and select the ground. And I always like to leave my Alias Dataset on here, showing points or maybe that surface, just so I can verify my settings are right before I convert this to a raster. So I've filtered, I'm only keeping the ground points, and I'm going to open that Alias Dataset to raster tool. So I'll hit Control F on my keyboard and search for the Alias Dataset to raster. And my input Alias Dataset is that Clemson Forest.LASD. And I'll save my output in my LiDAR results geodatabase. And I'm going to call it, I already have Forest DEM. So I'm going to call it Forest_DEM. Click Save. We can leave the binning, average, and linear options. We want to go down to cell size and select a 1 for our sampling value. All right, so our output grid, once I click OK, will be a 1 meter resolution elevation grid. And I'll close my dialog, turn off my Alias Dataset just to view my results here. Does everybody's look like this? Does anybody's not look like this? We're good? All right. So now let's make our surface model. I'll turn on my Alias Dataset, go to my filters, and select the first returns. And then run that Alias Dataset to raster tool again. So my input is the Clemson Forest Alias Dataset, my output raster. I'll save in my LiDAR results geodatabase and call it Forest_DSM. And save. And I'll set my cell size to 1 meter. And then click OK and run. So now if I close that, turn off my Alias Dataset and view the results here. Looks pretty good. All right. So the next thing we'll run is the minus tool. So I'll search for minus out of the Spatial Analyst tool set. And so this is going to subtract input raster 2 from input raster 1. So what do we want to specify as input raster 1? Either one is fine. They're basically the same tool. Yeah, there's a lot of the same tools are in the 3D Analyst and Spatial Analyst. If you have to purchase an extension and you don't need one or the other, they both provide a lot of the same functionality if you can't afford both of them. So what's our input raster 1 going to be? So if I click here in my box, it gives me this, and I show that tool help, it tells me the input from which to subtract values in the second input. So what were you saying, Joe?
I would say DSM.
Our DSM is going to be our highest one, forest DSM. And our input raster 2 will be our forest DEM. And I'll save the output in my results geodatabase, and I'll call it something other than, I'm calling it canopy_height. And then save. And then click OK. So here's our height raster. We can see there's some discrepancies. We have some areas where our DEM was higher than our DSM. We have negative values. We also see our highest value of 65 meters. So if we just look at our data, I'm going to switch on my Alias Dataset. For you forest people, where do you think, or can we identify areas we think would be appropriate habitat? Say 5 to 10 meter tree heights. Like where do you think those are going to be? I'm going to switch on my Clemson Forest LAS dataset and then just open that 3D view. See if that'll help. Are there any particular areas you think are going to have those trees? Well, let's adjust the symbology of our height raster here. We're going to classify the symbology rather than use a stretched value. So we're going to say anything from 0 to 5 will be a particular color, 5 to 10 a contrasting color, and anything above 10 will have as another contrasting color. So if I open my layer properties for this canopy height and go to symbology, here we're going to do classified. And let's set our number of classes to 3. And then we're going to classify and do a manual classification scheme. So my classification method will be manual. My break values are going to be 5, 10, and then the maximum in the data. So I can see here's my histogram of values. It's just going to grab that one particular range we're interested in. And then I'll click OK. So now if I click apply, anything that's gray is our appropriate habitat. So let's change our symbology a bit. For the negative 23 to 5, I'll double click on this black box. And I'm going to select a dark green. For my 5 to 10, I'm going to pick something contrasting, maybe a bright orange. And then my 10 to the maximum, I'll just select a light green. and then click apply. So there we have it. Where are you going to send your team to go try and find these nests? I think if it were me, I'd probably start here in this area here at the center, or maybe start looking towards the edge out here. Okay, so that's one way of solving the problem. We've subtracted our two rasters to get this canopy height raster. Let's try reclassifying our source data. So if I turn on my Alias Dataset, I'll turn off my other rasters here, and I'll view this as a classification code. Right, we have unassigned, we have ground, noise, model key, rail, water, just like we did in the other data set. Let's add 3 new classification codes, say low vegetation, medium vegetation, and high vegetation, and actually assign the points themselves a code where our medium vegetation is going to be these trees 5 to 10 meters high. And those are going to represent where we would have our ideal habitat. So we need to go to our search bar. We'll search for the LAS, sorry, what's the name of the tool? Is classify LAS by height. So we're going to do classify LAS by height. And what this tool is going to do is permanently change those LAS files. Right? So it's going to go through and change the classification codes in our data. So just keep that in mind if you run this tool. It's going to be a permanent change that's not easy to undo later on. So we're going to use this Clemson Forest reclass LAS dataset, which is a copy of our data that I've already created here. So our input LAS dataset will be this Clemson Forest reclass. So here it's asking for a ground surface classification code. And so we just want to use any of our ground points. So it's first going to estimate the ground elevation all throughout the area of our data set. And then it's going to compute how high each point is off the ground and assign it to class code 3, 4, and 5, which are low, medium, and high vegetation. And it's going to use the heights we specify here on the right. So our height from ground field, we're going to set 5 to be the upper limit for class code 3, or what it already was. We're going to change the upper limit from class code 4 to 10. And for class code 5, we're going to do the maximum in our data, which is, I don't have it in front of me here, but if I remember right, it was around 60 something. So I'll say 65. So any of these points that are going to be tagged with code number 4 are going to be those medium elevation trees, the one we're interested in. And here, let's check the box that says compute statistics. So this way, once the processing is done, it's going to automatically update the statistics for that data set. And we won't have to do it ourselves. So then let's click OK and run the tool. And mine says it finished quickly, but not taking a while to run. Is it really 100%? Did anybody's finished yet? Yeah, I don't think the status bar really matches how far it is in processing. But we'll just be patient here. So once this tool finishes, if you remember, we'll probably have to remove this Clemson Forest reclass data set from the data frame and then add it back in so that it will see those changes made to the statistics. Any minute now. There it goes. Okay, so if I close my dialog here, I'm going to remove Clemson Forest reclass from my data frame, switch off the other Elias dataset, go to my catalog, drag and drop Clemson Forest reclass again. And now if I change my active Alias dataset layer and change to the classification view, I can see those codes: low vegetation, medium vegetation, and high vegetation.
Where was the Clemson?
So on mine, it's using this bright green color, or not the palest green, but this bright green color to show that medium vegetation, which I guess I didn't quite set my colors quite the same here, but from my raster, I see those same points, the same locations here. But now I have all that cool functionality of working with an Alias dataset. Let's say if I wanted to do a 3D view on this one particular area where I see a lot of those trees. Right, I can go in my 3D view, see a little bit more about the terrain, or I can do a profile view through it. Say, take a profile through my trees. I can make measurements on them from here. I can do all sorts of cool stuff. So 2 different ways of approaching that same problem. Questions, comments, observations?
I don't think mine did that.
Don't think so?
Yeah. It says it completed it, but back up.
Did you remove it from the data frame and add it back?
The reclass.
Yeah. And go here and select. First, we need to make sure we're activating.
Where is this? Yeah. Yeah. Okay.
Yep, I think the key is we just need to make sure we activate the right data set. So yeah, we just need to make sure we're selecting the right data set here on the Alias Dataset toolbar that we're filtering. So we filter displays.
It just closed.
Oh.
I don't know if I just
All right, yeah, we're almost out of time to wrap up here. All right.
The program says we're done.
Yeah.
ArcMap decided this weekend.
ArcMap decided it's had enough. All right. So if you're interested in any of these other examples, they're in that tutorial document. If you ever have questions, feel free to contact me about them. So the summary points for today, these are the things I wanted you to take away. Do you think you could create an Alias dataset after you leave them? Right, we create a new Alias dataset just like a shapefile or a featured class, and then we add the Elias files on our computer. And from the properties, we can calculate and view the statistics of the data here. So we explored different tools for visualizing our data in 2 and 3D, and then learn how to use that Alias dataset to raster tool to create these elevation and surface models out of our data. Unfortunately, I didn't have time to go into classifying raw point cloud data, but just give you some examples of ways we can use our 3D LiDAR point cloud data. So here in our forested area, we can quantify the canopy height, and then also give you a quick intro to arc scene in 3D GIS. If you want to obtain LiDAR data, I've mentioned a few times now, South Carolina has very nice data coverage. You can download them all from NOAA's Digital Coast or USGS Earth Explorer. I think you can do it through the DNR's data portal, but that thing is really not fun to use. So I would refer you to NOAA or USGS. They have a nicer interface. Open Topography is like an open source network. They have LiDAR data for a lot of places. NEON, or the National Ecological Observatory Network, measures LiDAR data. We have some of the NOAA or DNR LiDAR data for South Carolina on one of our network drives that you can access pretty easily. I can help you with that if you have questions. There's lots of additional topics and bringing LiDAR data into ArcGIS, ways of bringing them into mosaic data sets, which pull different data sources together and stitch them on the fly. So you can incorporate point clouds into rasters or multi-resolution terrain data sets. So there's lots of additional topics. If you're interested, reach out. We can create a new workshop or tutorial for those. That's all I have. So thanks. Please fill out this survey before you leave today. I'll email out the link to where you can download all the data. It's a very big file. You remote participants know it's probably over 2 gigabytes of point clouds for this workshop. Thank you all for coming. The next workshop is Intro to ArcGIS Online and Story Maps. So we did a quick intro to ArcGIS Online last week. We'll use the mapping and analysis tools in more detail next week and show you how to build story maps with these template websites. And then we have Tableau the week after that, then spring break. And then our final workshop will be how to use drones or unmanned aerial vehicles to capture geospatial data. Using just a camera mounted to a drone, you can create updated aerial imagery and point clouds similar to LiDAR data. Not exactly the same, but a very cool data set, as well as terrestrial laser scanning or LiDAR scanning using our tripod mounted scanner. We'll give an introduction to that. So, thanks. Enjoy your weekend. I hope to.